Hi everybody and welcome back to our FreeFlyer Fundamentals training video. This is part 2 of 3, so if you haven't already completed part 1, please go back and do that now. We're going to be picking up right where we left off. In this section of the training, we're going to be talking in more detail about the STEP command, creating Ephemeris files, and working with lists and formation objects in FreeFlyer. And for our hands-on examples, we're going to add a second spacecraft into our mission plan and add the GPS constellation. Alright, let's talk a little bit more about the features of the STEP command in FreeFlyer. As you've already seen, once you've set up your spacecraft's initial orbit and initial attitude state, you propagate that forward in time using the STEP command. There are 2 different ways that you can use the STEP command. The first approach is to step the spacecraft one step at a time using the step size that you set in the spacecraft's orbit propagator. You'll often use this approach inside a while loop in your FreeFlyer mission plans, where you're propagating the spacecraft forward until an end condition is met. The second way to use the STEP command is to step to a condition, such as an orbit condition that exists built in on the spacecraft object, like stepping to the spacecraft's orbit apogee or perigee. You can also step to a specified epoch, or other condition that you specify, such as true anomaly equals 150 degrees. And then you can also combine different stopping conditions using the and or keywords. An important note when working with FreeFlyer is that if you're working with multiple spacecraft in your mission plan, you need to always ensure that the epochs of the spacecraft are synced. You can do this using the syntax example that you see here. For example, you're stepping spacecraft 2 to the condition where spacecraft 2's epoch is equal to spacecraft 1's epoch. This is necessary to ensure that all the output data and visualizations that you generate are evaluated at the same epoch across your different spacecraft objects. It's important to remember to keep your spacecraft epochs all in sync. FreeFlyer isn't going to propagate your spacecraft for you without you telling it to, and so the responsibility is on you as the user to make sure to use the STEP command to propagate each of your spacecraft to the correct time. Next, we'll cover how to create an Ephemeris file in FreeFlyer. We use the FreeFlyer Ephemeris object to generate Ephemeris files and attitude history files. These can contain various combinations of position, velocity, acceleration, as well as attitude data, angular velocity, angular acceleration, clock bias and drift, and covariance. Here you can see the Ephemeris object editor, which lets you choose the central body for the Ephemeris data, as well as the type of information that will be included in the Ephemeris using the checkboxes that you see here. Once you've configured your Ephemeris object, you'll use the put command to add the spacecraft's state vector into the Ephemeris. You can call this multiple times. For example, in the screenshot you can see that we are propagating the spacecraft in a while loop, and at each step we're putting the spacecraft state into the Ephemeris object. Once the Ephemeris contains all the state vectors that you want, you can use the put command one more time to export the Ephemeris to a data file. FreeFlyer has built-in support for exporting Ephemeris files in our own FreeFlyer format, the stk.e format, the ccsds OEM format, and some others. The FreeFlyer Ephemeris format also lets you specify custom columns of data using any numeric string or time values that you want. You can also specify custom column delimiters, and you can specify the interpolation method to use for each column of data. The Ephemeris file format also supports handling discontinuities, so if you have a maneuver contained within the Ephemeris, you can mark the beginning and end epoch of your maneuver so that FreeFlyer won't attempt to interpolate the states across that discontinuity. You can also specify comments for individual state vectors that will be saved in the file. Next, we're going to dive back into our hands-on example, where we're going to start from the mission plan that we began building in part 1 of this training video, and we're going to expand on it by adding a second spacecraft object. In this scenario, we want to generate a high-fidelity Ephemeris for this orbit. We also want to compare the differences in the orbit propagation depending on whether we use the default FreeFlyer force model compared to a higher fidelity force model configuration. So we're going to set up a second spacecraft object that will let us compare 2 different force models, and will generate an Ephemeris capturing the propagation of the higher fidelity model. The plan will be to add a second spacecraft object to our mission plan and update its force model to include higher fidelity gravity and atmospheric modeling. We'll synchronize the 2 spacecraft using a STEP command, and we'll compare the force models using an orbit separations plot, finally we'll generate an Ephemeris file. The first thing we want to do is go to our mission plan, edit Spacecraft 1, go to its propagator page, and set the step size to 30 seconds. This will simply update our output views and plots more frequently for smoother lines. Next, we'll add a second spacecraft object. We'll double-click on Spacecraft 2, and on its propagator page, set the step size to 30 seconds to match Spacecraft 1, and then on its force model page, we're going to make some updates. We'll select the Earth in the list of available bodies, and we'll update the Earth's gravitational potential field to use a 20 by 20 field instead of the default 4 by 4 field. We'll also check the box to turn on lift modeling, and we'll change the atmospheric density model to Jacquia-Roberts. We'll also turn on the box to model solar radiation pressure. I'll demonstrate those steps quickly in my copy of the FreeFlyer mission plan. I'll double-click on Spacecraft 1, go to its propagator page, and reduce the step size to 30 seconds. Then I'll add a second spacecraft object, double-click on it to edit. I'll go to its propagator page as well and set its step size to 30 seconds. Then on the force model page, I'll make sure the Earth is selected, and I'm going to change the Earth's gravitational field to use a 20 by 20 spherical harmonic field. We'll also turn on lift modeling. We'll change the density model to Jacquia-Roberts. We'll use the default settings for that model, and we'll turn on solar radiation pressure modeling. Now that we've set up these two spacecraft objects in the same orbit but with different force models, we'll add a plot command to illustrate the orbital differences that accumulate because of the differences in the force model. You can use either the plot command GUI or a freeform script editor to enter this plot into your mission plan, where we'll have elapsed time on the x-axis, and then on the y-axis we'll have 3 series showing the along track, cross track, and radial separations between the two spacecraft. Then we'll also add a step command into the while loop after the step command for Spacecraft 1 to synchronize the epochs of the two spacecraft. I'll demonstrate this by using freeform script to enter the plot command and the step command. It's always a good practice to enter a label for your freeform sections. And I'm going to use a separate freeform to enter my step command because I want to keep the two step commands together. I'm going to retile the screen just to illustrate what's happening here. Inside my while loop, I have various different commands that are generating output. Then I have a command to step spacecraft 1, and then I have my command to step spacecraft 2. Inside of that freeform, I'm using this stopping condition where I'm having FreeFlyer propagate spacecraft 2 until its epoch is equal to spacecraft 1's. Now, to reduce the number of output windows that will be shown next time you run the mission plan, you can go ahead and comment out the report and plot commands that we added in the previous parts of the training. So for freeform-based commands that you typed in, you can just type 2 slashes at the beginning of the line. And for GUI-based commands, you can click in the column to comment those lines out. And then we'll run the mission plan again to see the plot of the orbital separations caused by the different force models. So I'll comment out those plots and reports from the previous hands-on problems and save my mission plan and run it. Now we can see the 3D view and the 2D map that are still only showing spacecraft 1. We haven't added spacecraft 2 into those views, but the plot at the top of the screen shows the orbital separations between spacecraft 1 and spacecraft 2 as they're being propagated for one day. They started out in the exact same orbit, which was the default orbit when you create a FreeFlyer spacecraft object, but we changed the force model for spacecraft 2 to include a higher fidelity Earth gravity model, lift in addition to drag. We are using a different atmospheric density model, and we're modeling solar radiation pressure. Those differences in the force model affect the spacecraft's orbit as it's being propagated, and so the plot shows the long track, cross track, and radial separations between the two spacecraft. Next, we're going to get some practice at creating an Ephemeris file from FreeFlyer. We're going to add an Ephemeris object into the mission plan through the object browser, and we'll add a put command inside the while loop. You can use either the put command GUI or freeform script to put spacecraft 2 to Ephemeris 1, and then we'll add a second put command after the while loop to put the Ephemeris to an FFEFEM, which is a keyword indicating what type of Ephemeris object to create. We want to create a FreeFlyer formatted Ephemeris, and then give it a file name, such as highfidelitypropagation.ffefem. And then we'll save and run the mission plan, and then go ahead and take a look at the Ephemeris file that's generated, which will be located in the folder where your mission plan is saved. Okay, now let's work through these steps. First, we want to add the Ephemeris object through the object browser. You can find the Ephemeris under the all alphabetical list of object types or under the spacecraft related list of objects. Then we want to add a put command inside the while loop, and this is going to be used to put the state of spacecraft 2 into the FreeFlyer Ephemeris object. So make sure that you've selected for type of put, Ephemeris object, and that your script preview matches what I have here, put spacecraft 2 to Ephemeris 1. Then after the while loop, we'll add a second put command where we want to put Ephemeris 1. The type of put should be a FreeFlyer EFEM, and then give it a file name, highfidelitypropagation.ffefem. Again, make sure that your script preview matches what mine shows here, where we have put Ephemeris 1 to FFEFEM and then the file name that you chose. Now save and run your mission plan. When it's finished running, find the Ephemeris file and inspect it in a text editor. Okay, I'll take a look at my Ephemeris object in my text editor. And I can see that it did create a FreeFlyer Ephemeris file for spacecraft 2. I can see the start and end time span of the file and all of the data points that were captured. For our next topic, we'll talk about lists and formation objects in FreeFlyer. You can create a collection or a list of any type of FreeFlyer object. You can set the number of objects in the list by setting the list.count, and then you can use array indices to access each object in the list. The script example shown here shows how you could create a list of ground station objects called DSN, set the count or the number of objects in the list to 3, and then access the first element in the list or the first ground station in the list using an array index of 0. And in this example, we're setting the display name for the first ground station in the list to Canberra. This is a very powerful feature in FreeFlyer where you can have dynamically sized collections of objects of any type, whether that's a collection of ground stations, a collection of spacecraft, a collection of matrix objects, or a collection of orbit determination processes, or whatever your analysis requires. FreeFlyer also provides the formation object, which is similar to the concept of a list of spacecraft. You can create a list of spacecraft if you want, but really the formation object just provides additional capabilities on top of what you could do with a list of spacecraft. With a formation object, you can propagate an entire constellation with a single step command. You can visualize the formation using a single view or map command without having to list out all the spacecraft that you want to show in the view. And you have a built-in option of whether to visualize each spacecraft in the formation as a simple point or as a 3D model. You can initialize a formation either with a 2-line element file. You can manually define the orbit states of each spacecraft in the formation through FreeFlyer script, or you can load in a Rhinex broadcast ephemeris or an SP3 precise ephemeris. Similar to what we were just discussing when working with lists of objects, you use square brackets to access the individual spacecraft inside of a formation. So let's get right back into our mission plan and add the GPS constellation using a formation object. In this analysis, we want to add a report of the number of GPS satellites that have line of sight visibility with your spacecraft over time. So we're going to import the GPS constellation using a TLE file. We'll add the GPS constellation to the 2D and 3D views. We'll add a step command to propagate the GPS satellites, and we'll plot the number of satellites in contact with spacecraft 1. So here are the steps we'll work through. We'll add a formation object and edit it so that its name is GPS, and its initialization source is a NORAD 2-line element file. We'll browse to the gps.tle file that you can access through the link provided with this video. And on the visualization page of the formation editor, we're going to change the point size to 5 pixels. Then we'll edit the view and map commands to add the GPS constellation to those two views. And in the object browser, we're going to set up 2 variable objects and call them I and numGPS. Okay, so I'll add my formation object, which again you can find under all alphabetical or under spacecraft related objects. I'll double click on my formation and change its name to GPS. And its initialization source will be a NORAD 2-line element file. I'll browse to the file that I downloaded to my desktop, the gps.tle file that you can access through our website or through the link that's provided with this video. And then on the visualization page, I'm going to change the point size to 5 pixels. I'm going to double click on the view command and check the box to also show the GPS satellites in the view command, and then the same in the map command. And then in the object browser, I'm going to add 2 variables. And I'll rename them I and numGPS. And if you want to rename an object, you can right-click on it to rename, or you can also just hit F2. Next, we're going to add some simple logic inside our while loop to count up the number of GPS satellites that are visible from spacecraft 1. We'll use a plot command to plot the number of GPS that are visible over time. Okay, so we'll continue by adding a freeform section that we'll use to count up the number of GPS satellites that are in view to spacecraft 1. We're going to use a for loop where we loop over all of the GPS in the formation, and if they're in contact with spacecraft 1, then we'll increment the counter numGPS, and then we'll show a plot of numGPS over time. So first we want to reset numGPS to 0 at the beginning of each time through the while loop. Then we have our for loop. And notice we're using the array index GPS of I to access an individual spacecraft within the GPS formation. We increment numGPS, and then we plot it over time. Before running the mission plan again, we'll also need to add a step command to synchronize all of the GPS satellites with the epoch of spacecraft 1. In this example, we're using a for loop to loop over all of the GPS satellites and synchronize their epochs to spacecraft 1's epoch. Once you've added this inside the while loop, then save and run the mission plan again. I'm going to use a separate freeform section to propagate my GPS formation, because I prefer to keep all of my step commands grouped together towards the end of my while loop. That's just a convention that I follow. And you'll notice here we're using a for loop to loop over all of the GPS spacecraft in the formation, and we're stepping each of them to the end condition where its epoch will be equal to spacecraft 1's epoch. And now at this point we can save and run our mission plan again. Now in the 2D and 3D views, we see not only our spacecraft object in low Earth orbit, color-coded cyan and orange depending on whether it's in shadow or in light, but we also see the GPS formation being propagated. We see the plot of the number of GPS that have line of sight visibility to the low Earth orbiting spacecraft over time. And we still also have the plot showing the orbital separations differentiating between the default FreeFlyer force model for the low Earth orbiter versus a higher fidelity force model. This completes part 2 of our FreeFlyer Fundamentals training video. Please tune in for part 3.